Why does a particle made of pure light potential seem to die even faster in the real world than our best equations say it should? In the energy filament theory, positronia is not a tiny, perfect textbook toy but an extremely fragile-to-loop filament dance that reacts to the local tension of the energy sea. So small shifts in that tension show up as a lifetime that is always just a little shorter than the ideal value. Positronium itself is simple to describe and very hard to hold onto. It is one electron and one positron, equal in mass and opposite in charge, pulled together by attraction and locked into a tiny bounded state, like a double balloon made of charge that inflates for a moment and then vanishes in a flash. In mainstream quantum electrodynamics, you can write down the whole story in exquisite detail: energy levels, allowed spins, annihilation probabilities, how many photons you get when it dies, and you find a very short but very precise lifetime, which everyone agrees should be the baseline. The trouble is that when you make positronia in the lab and measure how long it actually lives, in gases, in solids, in vacuums, and in clever traps, the answer keeps coming out a bit shorter than the pristine calculation. The gap is tiny and you only hear it with very high precision experiments. But it refuses to completely go away even as devices and analyses improve. The honest mainstream reaction is to say the obvious: this is a brutally hard measurement. Every material and background effect matters, so there are probably residual systematics we have not nailed down yet. In this picture that may be partly true, but it may not be the whole story. Here, electrons and positrons are not hard little beads. They are ring-shaped filament structures in the energy sea. And when they form positronium, they do not become a rigid dumbbell. They twist into a brief, highly tuned shared texture, a choreographed short program that is destined to end in annihilation. That pattern is very tight and very delicate, changing the tension of the surrounding sea by a tiny amount and the way the two loops bounded, swirling and phase lock shift slightly. Those shifts do not rewrite everyday chemistry, but for a system that is only supposed to live for nanoseconds, they are enough to turn just long enough to finish the dance into "we dropped out a few beats early." You can picture two dancers performing the same routine on different floors. On a perfectly firm, flat stage, they can repeat the choreography and squeeze out every step before stopping. On a softer, slightly springy floor, their footing changes. They waste a bit more energy. Their timing drifts and the same routine ends a little sooner. Add a floor that is gently vibrating and the music keeps slipping under their feet. The dance does not collapse dramatically. It simply ends before the ideal last pose. In this view, the energy sea's tension is that invisible floor, the medium, its density and microstructure. And any local fields or fluctuations are different ways of changing how stiff, bouncy, or noisy that floor is. For robust filament structures, those differences are just background styles. But for positronium, which is already balanced on the edge between bound pair and pure light, they are enough to decide whether the system makes it to the theoretical endpoint or bows out a few moments early. So the stubborn observation that it always dies a bit sooner does not have to scream the theory is wrong. It can be whispering that the theory was built on a perfectly uniform mathematical floor, while the actual dance is being performed on the uneven, slightly shifting floor of the real energy sea. In this language, real particles gently evolve with tension, and positronium, as an ultra-sensitive, ultra-short-lived structure, simply amplifies that evolution into a measurable lifetime deficit. The positronium short-life mystery and becomes one more microscopic clue that when the universe's tension changes, some particles choose to answer with how long they can survive before turning into light. Tap follow, share it on New Physics, Clear Universe.